So one thing we're going to see later is the function f of x equals e to the x. If you notice, if we kind of analyze the function's graph on the intervals that looks like to be doing something, the derivative looks like it has similar characteristics to the function itself. And we're going to see in the next section that the derivative of the function e to the x actually is just e to the x again. So that's kind of cool. We're going to see that. But here's an example of a function where it's increasing without bound. It doesn't slow down again. It doesn't turn and reach a horizontal asymptote. The end behavior is it just keeps increasing to infinity. So that means that the derivative is going to also be positive and increasing to infinity. So I wanted to also talk about alternate notations. So we've seen f prime of x a lot already. And so there are a couple of other ways that you're going to see this expressed. df dx means the derivative of f with respect to x. Y prime is another notation for f prime. dy dx, which is change in y over change in x. And then delta y over delta x is an expression for the difference quotient, and the derivative is the limit as delta x goes to 0. There should be an x there. Delta x goes to 0. So these notations with the fractions are called Leibniz notation. And they're not really fractions per se, but they look like it to us. So since the derivative is derived from the function, you can think of it as there being a differentiation operator that acts on a given function. So here are other notations that express finding the derivative as the differentiation operator. So this notation, d dx of f of x, means take the derivative of f of x with respect to x. Same with this capital D, or d sub x. And then finally, this vertical bar. So you might see the derivative with a vertical bar, or even just a regular function. This vertical bar with a subscript that says x equals some number means evaluate this function at this number a. So for example, we said a couple slides ago that the derivative of e to the x was just e to the x. So what does this mean? Take the derivative of e to the x and then evaluate it at a. So since the derivative was just e to the x, I just need to evaluate e to the x at a, and I get e to the a. Remember, e is just a constant. Even though it's a letter, it's just a constant. It's some number between 2 and 3. So one of the examples that's going to crop up in the homework is given a function, find where it's differentiable. So given this function, that's a quadratic function. So we know that its domain is minus infinity to infinity. So if we find its derivative by taking the limit definition of the difference quotient, we end up with this linear function 5x plus 6. So we know that the domain of a linear function is also all real numbers. So this means that f is differentiable everywhere. And this is the case with all polynomials, actually. They're always differentiable everywhere.